In this video, what I want to do is some chapter 6 examples. So let's just jump on in. So chapter 6 starts with example 1, which is about iPhone battery life. And it says, suppose that the iPhone battery life is normally distributed with a mean of 4.1 and a standard deviation of 1.7, both in years. What's the probability that a randomly selected iPhone will have to have its battery replaced in 5 or fewer years? And so what we're going to do for these is let me draw a graph. Let me first say that we're assuming that iPhone batteries are normally distributed. Of course, they can't be perfectly normally distributed because the normal distribution should go from negative infinity to infinity, but normal distributions can often be good enough, so this is a good model. Okay, so we're assuming that they're normally distributed, even if that doesn't exactly make sense for, say, negative values, but that's okay. So in other words, we're assuming that where this does make sense, it's a good model. And then given that model, we want to know what's the probability that a randomly selected iPhone will have to be replaced in 5 or fewer years. And so the idea is that we want to think about the cutoff 5. And then what we're asked to do is we're asked to find what's this area. So the area from 5 all the way down to negative infinity. Okay, so really this includes stuff over here too, even if that doesn't strictly make sense for the example that we're studying. And there's a few different ways that we can do that. I'm going to do this with R. You can do this with the probability tables, the standard normal table that's on the handouts on Canvas. So you can do it that way. I think it's I think it's just better. It's a little bit more versatile to be able to understand R and to have R used for this purpose. So if we're going to use R, the way that we would do this is a P norm. Right, because we're talking about the cumulative area up to a certain point. That certain point is 5. We're assuming that we have a model where the mean is 4.1 and the standard deviation is 1.7. Okay, and so if we type that in to R, what we're going to get is 0.7017. Let's just say to 4 decimal places. Okay, so that's going to be the probability that a randomly selected iPhone battery will have to be replaced in 5 or fewer years. Okay, so about 70%. Notice that this agrees intuitively with what we know. So for example, we know that the area up to 4.1, so this area all the way to the left of 4.1, or equivalently the area at 4.1 and to the right, both of those regions have area 1/2. So the fact that 5 is a little bit more than the mean means that if we're talking about the cumulative probability, that'll be whatever this area is plus 1/2. And that agrees with the fact that our answer is above 1/2. So that's, again, just a good intuitive gut check to make sure that we have the right answer there. But that's it. That's all we have to do. There's a 70% probability. So moving on. So number 2, suppose that the replacement times, again, same assumptions. We have replacement times for battery phones are normally distributed with a mean of 4.1 years and a standard deviation of 1.7 years. Different question though, obviously, if we want to provide a warranty. So suppose that you are Tim Cook and you want to figure out what's the warranty got to be on the iPhone so that 98% of the iPhone users need a replacement after the warranty expires. Is like the evil corporate question, right? So you want to make sure that most of the phones will need to be replaced after the warranty expires. How long should your warranty be? That's the question. And so what you want to do is you want to figure out, it's going to be kind of the same idea. So you're going to take the same curve. I think it's just useful to see a graph here. We're going to have a mean of 4.1, standard deviation of 1.7, whatever that means. Come on. Okay, and then what we want to do is we want to figure out how long should the warranty be so that 98% of the phones need to be replaced after the warranty expires. So we want to figure out what is this value so that this area over here is 0.98. Okay, that's what we want to do. And there's 2 ways to do this. I think the easiest and most straightforward way is to think about, well, if this area over here is 0.98, what's this area? Well, 0.02, because we know that the total area under the curve has to be 1 because it's a probability density curve. And what we could do then is we could use R and type in Q norm of 0.02. And again, we have a mean of 4.1 and a standard deviation of 1.7. And when we do that, what we get is 0.6086. Okay, so a little more than half a year. So that should be, you should have, and this is in years. Okay, so after 0.6 years, so that's like 7 months basically, 7 months and a few days, the warranty should expire. And then after that point, 98% of the iPhones will need to be replaced after the warranty expires. Okay, so that's the idea. All right, number 3. This is just a straightforward standalone question here. Suppose that you have a standardized test. This is actually modeled after the SAT, which is normally distributed with a mean of 400 and a standard deviation of 80. So what score do you have to be in the 80th percentile? And what it means to be in the 80th percentile is that you score better than 80% of any randomly selected person. So here our mean is 400. You want to know to be in the 80th percentile is this value x naught, so that the area under the curve to the right over here is 0.2, or equivalently the area under the curve to the left is 0.8. And that's what it means to be in the 80th percentile, is that you're going to score better than 80% of the other people taking that test. And so how could we do this with R? Actually pause the video, think about it, try it, and come back, see if you got this right. Okay, so hopefully you paused, and what did you get? Okay, so hopefully you paused, and what did you get? Well, what we want to get is, we're going to use the Q-norm function. This is Q-norm 0.8, the mean is 400, the standard deviation is 80, and if we do that, we will get 467.3297. And notice that that again agrees with our graph, right? We know that it should be a little bit more than 400, and in this case it's 467. Okay, so that's how the graphs can be useful for us. All right, example 4 and example 5 involve the same idea, that what we're going to do is, imagine that you're running a distribution center, and your job is to take cereal that was produced and put it in boxes. And the machines are set up so that you don't get exactly the same amount of cereal in each box. You get roughly the same amount, and the boxes are marketed as 24-ounce boxes of cereal. And so it turns out that the amount of cereal that you get in any particular box is normally distributed, okay? And the standard deviation of that distribution is 0.25 ounces, so a quarter of an ounce. We do not know what the mean is, okay? We actually want to figure out what is the mean, and what does the mean have to be in order for most of the boxes to have 24 ounces of cereal or more. Okay, so what does the mean have to be in order for, when I say most, I mean 99.5% of the boxes in this case. Okay, so we want to know, what does the mean have to be in order for 99.5% of the boxes to contain 24 ounces of cereal or more? This is a slightly tricky question. And so what we're going to do is we need to know two things. We need to know that the standardized score, Z, remember, is x minus mu over sigma. And additionally, we need to know under the standard normal curve, okay, so under the standard normal curve, so let's draw that over here. So this is with mean 0 and standard deviation 1. You want to know where's the cutoff, so that to this cutoff and to the right, 99.5% of that area lies. So in other words, you want to know where's the cutoff, so that this area over here is 0.995, or equivalently, this area over here, the red area, is 0.005. These are not to scale, obviously, but just so that we can see it a little better. And we want to know what's that cutoff. So there's 3 ways that we can get this number. The first is using R. We could just type in Q norm of 0.005. Remember, when you don't put the mean and the standard deviation, it assumes that you're working with a normal distribution, which is exactly what we are, and this turns out to be negative 2.576. Another way that you could do this is you could use the chart, the normal distribution table that we have on our formula sheet. Okay, so you could do it that way. Or there's a third way on the handouts page on Canvas. By the, I need to figure out where it is actually. Somewhere on that sheet is the values, and we call these z sub alpha. What we're looking for is z sub 0.995. In other words, the cutoff value so that the area to the right is 0.995, and that would be negative 2.576. Okay, so this is really just another notation to talk about the same value. So let me just write it like this. Okay, and then that's the cutoff. All right, the other thing that we need is we need to go back and think about the question here in the context of what we had. A machine fills 24-ounce boxes. We want to figure out what does the mean have to be so that 99.5% of the boxes have at least 24 ounces or more of cereal. In other words, what we have to do is we have to figure out, we're going to have a new table here. So this was for the normal distribution. This is for the cereal. Okay, so what we're going to do is we're going to figure out what does the mean have to be in order for this cutoff here to be 24, so that the area to the right of 24 is 0.995. I hope that makes sense the way I said it. This again will not be to scale, but the idea is you want to figure out what does the mean have to be, in this case we'll call it mu, so that the area under the curve to the right of 24 is 0.995. That's essentially what we're asking here. And so what we can do is we have 3 of the 4 terms. Okay, we have z, x, and sigma, and we need mu. And so this is going to become, let's see, z is negative 2.576. X is what? X is 24. We don't know what mu is, and we're told that the standard deviation is 0.25. And it turns out that when you solve for mu, this is now a simple algebra problem, when you solve for mu, so you multiply both sides by 0.25, subtract 24 from both sides, divide by -1, what you're going to end up with is mu is 24.644. So it turns out that that's how you have to calibrate the machine, is so that the mean is 24.644 ounces if you want 99.5% of the boxes to have at least 24 ounces or more of the cereal. Okay, so that kind of tells you how you have to calibrate the machine to do that. Okay. Number 5, same idea. Okay, you have a machine that fills 24-ounce boxes of cereal. Again, it's not exactly 24 ounces. It's normally distributed. And it's normally distributed with a standard deviation of 0.2 ounces. What does the mean have to be in order for 0.2% of the boxes to contain more than 24.5 ounces of cereal? So this is kind of the flip question. Before, what we wanted to know is what did we have to set our machine at so that most of the boxes had at least 24 ounces? Here we want to know, how do we have to calibrate the machine so that most of the boxes don't contain that much cereal? Okay, so it's a similar question, but kind of the opposite end of the coin here. And so what we're going to do is a very similar calculation. I'm not going to draw the graphs anymore. I think we're okay with that. We have to figure out what's the cutoff so that the area under the curve to the right of that is 0.002, because it's 0.2%. That's going to be Q norm. of 0.998, which is 2.878 according to R. And again, what we're going to do is solve for mu. So we're going to solve 2.878 equals 24.5, because that's our cutoff now, minus mu over 0.2. Let me just say one extra word here about why I changed this 24 to a 24.5, and that was, of course, because of the question. But remember what we were looking for. If we think about the standard normal curve, we want to know what's the cutoff so that to the right of this point, this area is 0.002. And it turned out that that cutoff was 2.878. Okay. And so what we want to do then, this is for the normal curve. We think about the serial curve. We want to know, what does the mean have to be if 24.5 is that same cutoff, so that the area under the curve to the right of it is 0.002, or equivalently, the area to the left is 99.8% or 0.998. So when we do this calculation, this is again just a simple algebra calculation. It turns out that the mean should be 23.9244. Okay, so this is like the ultimate cheap measure of a corporate overlord here, right? We want to know, what does the mean have to be so that we don't overfill the cereal too much? Okay, so again, a reasonable thing if you don't want to waste too much cereal there. Anyways, finally, number 6. Again, number 6 is just a question about a standardized exam. The idea here is that you have 1,000 students, and they're going to take an exam, and the exam is going to be normally distributed with a mean of 70 and a standard deviation of 10. And so we're going to randomly select a student from this group, and we want to know what's the probability that the student's grade is at least 80. And there's 2 ways to do this. One way to do this is to do 1 minus p norm of 80, 70, 10. Another way to do this is to do the p norm function, 80, 70, 10, but now we want the upper tail. So we would do lower dot tail equals false, or just equals capital F. And when we do that, we're going to end up with 0.1587. Okay, so 0.1587. Okay, and that's it. We're done. Now find the probability that the student's grade is less than 50. Here, we'll do p norm 50, 70, 10. We don't need to do anything else because it's the probability that it's less than or equal to 50. So that cumulative probability part is built into R. So that would be 0.0228. Find the probability that the student's grade is between 50 and 80. So here we would think about what's the probability that it's less than 80 minus the probability that it's less than 50. So that'd be p norm 50, 70, 10. And when you type that in, you'll get 0.8186. And then finally, approximately how many students have grades greater than 80 on this test? What we would do is we would take the percentage from part A and just multiply by 1,000. The percentage from part A being 0.1587. So just rounding to the nearest integer, this would be 158.7, or approximately 159 students. Okay.